So this slide just makes the point that you need to pick a sensor which has a cost appropriate to the project, and then you have to design the software around it. It's always true that if you buy a costly sensor, you can probably make the job easier, but you have this tussle when you're making a practical product that you need to, the cost has to be right for the application. So this is an important topic because people don't understand terminology. So what is path planning versus trajectory planning, also known as navigation? So path planning is like a high-level operation. It is based on spatial considerations. So time is not part of it. So typically, the most common path planning algorithm is A star, and what it will do is, given where you want to go and where you are, it will join these 2 points by connected straight line segments. So these straight line segments will be meeting at an awkward angle. It doesn't care. So it just basically draws something like this. It is similar to what Google directions look like, go to this intersection, turn right, right? It doesn't tell you, how you're supposed to drive to avoid traffic. It's just saying go to the next intersection, and then turn right, and then turn left, and so on. So it is up to you to curve the path accordingly. That happens in the trajectory planning phase. So path planning is basically based on gap analysis. In other words, they figure out that the robot, with some added margin for safety, will be able to negotiate the gaps. Now that's not a good assumption, because see the difference between having a Volkswagen Beetle and driving an 18-wheeler truck? So the gap may be okay for both, but I won't be able to turn an 18-wheeler truck through some of those gaps. So often it happens that if you follow the path plan, then you run into a situation where you find out that your vehicle cannot turn. So what you'll have to do is abandon the path and say, give me a new path. So path planning doesn't care about whether you have kinematic, dynamic considerations. When you put the two together, it's known as kinodynamic. So kinodynamic is a word that covers both kinematics and dynamics. So path planning does not take into account kinodynamic considerations. Trajectory planning has to. So it's like you're separating the problem into 2. You're first threading straight line segments from the starting position to the final position through an array of obstacles. And then you're figuring out what is x, y, and t. So trajectory is literally x, y, and t, or x, t, y of t. And that is your driving rule. So somebody's telling you, drive according to this rule. And then you'll find out whether the path was good enough for you to go through, or else you have to replan at some point. Obviously, it doesn't happen on the roads, right? It happens in something known as open field navigation. We'll get to that shortly. There are 2 forms of navigation. One is open field, and the other is roadway. So roadway navigation is the one that is most like cars driving on the road. So you can't just cut across fields, right, to join another road. You have to follow the road and find the crossings. But in open field navigation, it's like a military problem. You have a tank or some other robot, and you can go anywhere you want to. Some of them go through houses. The tanks, sometimes, just run over houses, because they have so much power. So there are some research literature that deals with path planning and trajectory planning as an integrated problem. Now, why don't people do that? Because that is the best approach. It's because it takes more time. So university professors can afford to do that, get a paper out of it, but it turns out that it's hard to implement those methods in the real world. So that's why they separate the 2. Path planning first, global, and trajectory planning is local. So literally trajectory planning, your trajectory may have to change, because if you have another car that is suddenly taking a turn in front of you, you obviously have to change the trajectory. So trajectory planning sometimes is dynamically changed. You use a control algorithm to say, okay, somebody's crossing the road now, and either you stop or you try to curve around. Okay, so this is what I was talking about. Two typical robot behaviors or car behaviors, whatever is the moving vehicle. One is goal seeking, and the second is obstacle avoidance. So it's as basic as that. You need to get to the goal in an optimal fashion, avoiding obstacles. So obviously it's an open-ended problem. There are many solutions, and that's why all these path planning algorithms, over the course of history, you find so many of them. So as the robot moves, it has to combine these two behaviors. Typically, obstacle avoidance will take precedence over goal seeking. You cannot run over an obstacle. If you have a tank, you might, but other than that, you have to go around obstacles. You cannot hit them. Now, if you had more time, and this was an elongated course, same number of hours but elongated, we could have done a homework on avoiding an obstacle and getting to the goal. It's not very difficult. You've seen how we are going towards a waypoint at the same time maintaining heading control. It's easy to then extend that to avoiding an obstacle and then getting back on track. So there is a behavior known as wall following, which we follow when the car is in a tunnel, which we follow when the car is driving in a lane, right? Which is never in India. But if you're driving in a lane, it is wall following. And if you're asking yourself, where is the wall? Where the lane lines are, imagine, you can imagine that there's a wall. That's what we're doing, right? The lane line becomes like an extended wall. So we are basically using wall following all the time. It's a very common algorithm to use. Yeah. So two types of motion: open field or point to point. So that is on the open field. You might do this on the battlefield, or when there's been an earthquake and everything has been leveled, you might not see any roads or anything, and then so you cut across and do whatever is necessary to fulfill your mission. Now this is something I'm repeating. The environmental status is never fully known. It's only partially known because you could have mistakes in the map given to you. So it's partially known. That's the best assumption. So accidents and congestion updates, well, congestion may be close to real time, but accidents, sometimes, both of them may be in real time, but typically it takes a few minutes to gather that information and then for Google to refresh their driving directions. Now, in going to the final destination, remember I told you it's the path is like straight lines, joined at odd angles. So basically there's discontinuity there. So if you have a robot that can stop and turn, you can do that, right? But a car cannot stop and turn because it can only drive into the curb, right? So a car doesn't have that ability to point towards the next heading. A differentially steered vehicle does, but cars are not differentially steered vehicles. So you have this need to dynamically adjust your trajectory, even though the path looks like this. And a common example of where you need to do that is, suddenly the car ahead may have stopped, right? So you look in your mirror and you go around. So you are dynamically changing the trajectory all the time. You're only given waypoints, but the waypoint doesn't mean that you can drive through a car that has stopped. So you may have to go around temporarily to get back on track. So all of those things you plan on the fly. It's local driving. It's in your local map. It's got nothing to do with the overall global path. You have to do these little maneuvers around obstacles that are suddenly showing up on the map, because they're not on the global map. Because obviously that's why the path went right through the obstacle, because dynamic cars around you, nobody can put on the path. So there is always an optimality criteria. You can't take all day. So you can have many criteria. Fastest is the one that most of us relate to easily. You want to get as fast as possible while staying within the speed limits. Shortest, and if you're saying, isn't the shortest the fastest? No, not necessarily. Because in the US we have freeways, right? The freeways are not the shortest distance to wherever you want to go, because they curve a lot. Because the freeways have often been built based on where land was available. So they go like this and so on. But the surface streets, in the US, the streets are laid on a grid. So the surface streets are the shortest way home, but they are slower. because the speed limit is less than what you can maintain on the freeways. So the two are different. And then you have safest. So the best example is maybe there's a road to the airport which is under enemy fire, but it's the shortest way to get there. But it's not the safest. So maybe you value your life and your equipment more than speed. So then you take a longer route which is further away from the scene of the battle. So safest, that's a good example. Now most economical. Now you may have a destination on the other side of this mountain. Is it better to go around or is it better to climb and come down? So when any robot climbs, it's using more energy. So if you're low on the battery, then probably it could be better that you go around the base of the mountain rather than go over. So how will you serve all these masters? So typically what is done is you create one criterion function, and this criterion function is like constant A times the first criteria, distance traveled, plus B times the second criteria, speed, and so on, safest and most second. So you come up with a composite criteria. The A, B, C, D, they should sum to 1. But maybe on a given day you want to allocate 0.5 weightage to speed. So then you make it 0.5 and the others maybe it's 0.2, 0.2, 0.1. So one of my students is using this in a PhD work because it's a very common thing to do. It's a linear combination of all of those. And if you only want speed, you just make that 1 and set all the others to 0. So you can get any one of the criteria either dominating or completely wiped out. So that's how you typically optimize. So we need a formal framework to solve such problems. And this is one of the earliest. You will find it in robotics textbooks. I don't think people use it now, though if you go on the internet, you'll find MATLAB and Python code, and it's kind of a good learning experience to download that code, set up something in Gazebo, and in terms of, I'll show you. These are the two classic examples for bug 1 and bug 2. So you can easily set up an obstacle like this, and you can actually run the code from GitHub. There are many GitHub sites with the bug 1 and bug 2 because they've been around forever. So what is the bug? What is this category of bug algorithms? So it's inspired by insect behavior. So when an insect needs to go somewhere and it hits an obstacle, it will follow the perimeter of the obstacle until it's around it, right? Then it will continue towards the obstacle. So that's what inspired the bug algorithms. It assumes two things. One is several things, but the most important one is that you can calculate the straight line distance from P1 to P2. Any 2 points, so goal is one of them and your current location is one of them. And so it assumes we have some means, and of course the bug doesn't calculate distances, but it assumes our robot is capable of calculating that distance. That is part of the algorithm. And then the robot can localize perfectly. The robot is considered a point object. In other words, it has no dimension. So that is a simplification, right? Because this was an early algorithm in textbooks only. It was not meant for implementation. So the robot is assumed to be a dot. That's it's a problem because when you're going through a gap between obstacles and the robot is not a dot, then you got to ask the question, am I going to fit here? Here you don't worry about it because it's a dot. And it's equipped with a contact sensor. Okay, so the basic strategy is move in straight line towards goal till we run into obstacle. Then we go around the obstacle, you can pick left or right, it's random, and continue towards goal. So we do assume that we have the map. This is not a case where the map is being discovered as you move. In the real world, most of the time the map is being discovered as you move, right? When you go around a corner, for the first time you see it there. You see, the new part of the environment and you put it on your local map. Here you assume that the whole map is known. So, listen carefully because bug 1 is different from bug 2. Ultimately, there's nothing to do with bugs, right? The only idea that we borrowed from the bug is it'll go towards the obstacle and then it'll either go left around the obstacle or right and get to the other side. That's the only behavior we copied from the bug. So start moving in straight line towards goal. So here it's going on a straight line towards the goal. If obstacle encountered at hit point, so here's the hit point, circle around it till best leave point is found. So you can go either left or right. Okay? It does not know how big this is. So if you were smart, you'd say, hey, I think it's better to go around this because the goal is closer to this side, right? But what if this island were like this? You know, extend this part of the island. So you don't really know. You have to guess and go left or right. So it goes, keeps going, right? And then why does it come back? Because it does not know the best leave point. It's saying, okay, what is the distance to the goal? What is the distance to the goal? What is the distance to the goal? And then it has to do all of the island before it figures out that this is the best. It's just an algorithm, right? No point in laughing at it because it's just an algorithm like any other algorithm. So computer scientists used to come up with algorithms and then they do math on it and prove the optimality and so on. So it has to do a second circuit because it does not know whether it will find a closer point than over here. Once it has done it once, then it knows. And so then it picks up this and does the same thing for WO2. See, it's going around it one more time than you would think is necessary. And then it goes to the goal. Is that okay? Now, look at bug algorithm 2. So before we go to bug algorithm 2, here's a situation that the robot is trapped and cannot make it to the goal. So typically you have to have some part of the algorithm which is stop trying. So you need what they call as heuristics. A heuristic is a common sense rule. So you need to add a heuristic in order to stop the robot from going around and around and around forever. Because what happens is, it starts from here, the first hit point, it decides to go left, and finds out that this is the best leave point, and then it can't go. So basically, you have to have a termination criteria at this point. So we need some shutdown logic, that's what I said. When to stop trying when reaching goal is not possible. Base algorithm fixes leave point, right? Add heuristic to terminate the effort. You have to add something to the code to terminate it. It's actually, it's fun. If you find code on the bug algorithm in MATLAB or Python, it's fun to actually run it because you learn a lot, about path planning and navigation. Notice the difference here. Fixed. So compared to bug 1, there's a fixed line between the starting point and goal, and it's not going to take off anywhere. When it reaches this line, it's going to take off. So right now you're saying, oh, it saved a lot of effort because it didn't try to find the shortest leave point. It just encountered the line from the initial point to the goal, and then it said, let me go towards the goal, and then it got stopped and it did it again, right? So it looks right now that this algorithm is better than bug 1. It's not. And this is where computer scientists have fun. They actually showed that bug 1 is optimal in certain conditions and bug 2 is optimal under different conditions. What are those conditions? It depends on the obstacle density in the environment. So they like proving these mathematical results, computer scientists. Okay, so this is, just watch. If you thought one was better than the other, you're going to be fooled because it's not an obvious answer as to which one is better. So you've got to watch carefully. So that's the obstacle. So this is bug 1. It finds the leave point, goes all the way around to find the shortest leave point. See, it marks that, but it's checking further. You see that? No, I bet you missed it. So it marks the leave point, but it can't tell that it's the shortest unless it goes all the way around. So see, it marks it, and then it goes all the way around. It's happy with the leave point, and then it'll again mark the shortest leave point because it knows it's going further away. So you know why it can't go? Because this part of the island may be like this, right? You may actually have a wall that goes very close to this. So that's why it's marking it. It can change it, but it doesn't have to. It goes all the way around, confirms that the first leave point was the best one, and it does it. And some statistics should pop up here. Yeah. So what they're doing is the Euclidean distance from the starting point to the goal is 200.6. the actual distance traveled is 546. So ideally you want a ratio of 1, right? You cannot get a ratio better than 1. Because how can you, have a path that is shorter than the Euclidean distance? You can't. If there were no obstacles, at least, you have to have the Euclidean distance. So here it turns out to have 546, which is a ratio of 2.7. Not bad. So bug 1, layout 2. Look at this. So they know that this is going to bring out the difference between bug 1 and bug 2. They know the creators. So here's the starting point, and there's the goal. So you see, they're following the bug 1 rules. The best leap point. See, it's updating the leap points. Can you see that? No? See, leap point, updated, and then it's going all the way around, following the bug 1 algorithm steps. It's not getting a shorter leap point, so the red dot is still there. And I think it's going to mark a leap point there, but it will continue. It's not going to take it. So that's why it's a problem with bug 1. It just sticks to the rules. So once it goes all the way around, it knows. And let's look at the statistics. It's 13.51 times. And now bug 2 on layout 2, I think. No, bug 2 on layout 1, sorry. Yeah, bug 2 did not do layout 1 yet. That's it, it's going to go. And you're going to get a nice ratio here, and you might think that, bug 2 is great. 2.01, which beat 2.7 something, or 5.6, I don't remember the number, but it was definitely higher. Now, bug 2 layout 2. Yeah. So it's going to work off the straight line. Look what happens there. That's part of the algorithm, right? You have to go left when it intersects the line, and it's going left. Again, it's going to go left, right there, because that's what the rule says. Again, finally it's going to make it. And it's going to be a huge distance, I bet. 65 times, right? So bug 2 also has the unreachable case, similar to bug 1. So you have to have a heuristic where it fails and you ask it to stop trying. All robots have this problem. A human being would know when it's time to give up and say that there is no path that I can use, right? But for robots, you have to create an algorithm, lines of code that do that, when to call it off, and so on. So, as I said, at first glance, you'll say bug 2 is better than bug 1 in every single instance, but it really depends on the situation. Bug 1 follows what computer scientists call an exhaustive search philosophy. It's going to try going around the island, thinking that it might find a shorter leap point. Bug 2 uses an opportunistic, these are all computer science words, also known as greedy strategy. And they can prove it, computer scientists, that for more cluttered environments, bug 1 will tend to perform better than bug 2. And also that if there's a solution, these algorithms will find it. If there's a solution, the algorithms not finding it is a problem when you implement robot navigation strategies. Because a human being can sometimes see that, so for a robot, you expand the robot by You expand the obstacles by half the radius of the robot. So that is an attempt to create a safety zone, right? But the very act of expanding the obstacles by half the size of the robot may close off a gap. And therefore, the algorithm might say there is no way, even though you can see it clearly, a human being can see that there is a way. Maybe you go slowly and you squeeze through. So you have this problem with robot algorithms, that avenues might be blocked off, whereas the human being will be able to figure it out. Now, of course, with the AI, we might reach a point where we can teach a machine how to think like that. But right now, these algorithms are quite stupid compared to a human being, and that's why a semi-autonomous mode makes more sense. Because I told you, I think on the very first day I said that in UK there is a pilot program where there's a guy in a central control room guiding these autonomous huge trucks. And so anytime there's a problem, he's able to see what is going on, take over and guide the truck through that sticky spot. Maybe it's the driving has to be very intricate, and he manages to get it through, and then he says, okay, go back to being autonomous. So right now you need something like that because the machines are not that smart. And this tangent bug, this is what happens in universities. Somebody comes and says, okay, I've got a better variation of it, so I just put it there. This one also has code available on the internet. So just a word about this, because this actually transcends just robotics. This is very important because when I was a student, when people throw the word optimal at you, you think of it as the word of God, that nothing can beat it, right? But every optimal algorithm is attached to the conditions under which the problem was defined. So optimal means the next question you should ask him is, what did you assume for the problem? So the optimality is tied in with the assumptions. Somebody else could have a different set of assumptions and come up with a different optimal. But the word optimal typically scares off everybody because they say, okay, he's found the best. There's no point in me doing any research because he's got the optimal solution. That's not true. So optimal often means that it is so from a certain perspective based on assumption or assumptions involved. We could have several optimal results. And maybe the optimal result is God. In the real world, you might not be able to implement it because of computational cost. So the optimal result that somebody came up with may in fact not be feasible. So people who work in research, mostly university people, they create these optimal solutions. Some of them are not feasible from the point of view of implementation. So then you ask yourself, if the optimal is not really an optimal, can I find a suboptimal solution which is fine, will work okay, right? Maybe it's not the best, but maybe it's close to the best. In fact, if you think about human existence, we often go through life doing exactly the same thing. When there's a crisis, we don't sit down and say, okay, give me a sheet of paper. I'm going to, think of all the possibilities. No, you kind of figure out on the fly because time is important, right? You can't afford to say, give me a day, I'll figure out what the best solution is. You might have to act immediately. So often suboptimal solutions are better than the optimal solution, which is actually a myth. There is no such thing as optimal solution. So suboptimal is what most engineering systems implement. So this is the other thing. The optimal algorithm might be based on assuming that your sensors are like the eyes of God or something. So the actual sensors may not be that good. In fact, they're definitely are not perfect. So the moment you take away that, then the optimal solution falls away. So if you are working with glasses, then suboptimal solutions are fine. I use glasses to refer to a suboptimal, like not so good sensor. That's what I mean by glasses. And so the suboptimal algorithm may actually be an advantage because it's quick, whereas the other one you might have to wait for an hour. So there are path planning algorithms which take a long time. But should you be moving? So there are other algorithms which say, okay, I'll start moving, I'll come up with a rough plan, and I'll start moving towards the goal, right? And then as I go, I will figure out, a good solution as I move. No point in sitting here and running a computer for 30 minutes to come up with the optimal solution because the assumptions of that algorithm may not be valid in practice. So in other words, the optimal solution is disconnected from your reality. So there's no point in going with it. So optimal scares off a lot of people, but there's no such thing really. So part B has the Dijkstra algorithm. The students are going to miss something. The Dijkstra is the classical graph search algorithm. So this one I just put it up one second. So this is a general overview of the terminology and theoretical underpinnings. It is not going to discuss the latest and the greatest, though you'll have a glimpse of that. So there are two categories of graph search algorithms. I'm sorry, path planning algorithms, right? And the latest and greatest is in the second category, which is random search as opposed to deterministic search. So till recently, most people were using the deterministic search. Now they're using random techniques. So essentially, let me give you a preview of that, though you'll see a slide. They essentially, from the robot's position, they throw out search nodes. They scatter it in a random fashion. And then from each one of those, they scatter some more nodes. And so kind of imagine like these fingers are reaching out, it's like search fingers reaching out into the space around obstacles. They make sure that anytime you assign a node, it does not land on an obstacle. So they have the means of doing that. So finally, a node ends up close to the goal, and then they're immediately able to optimize and say, okay, use this finger, this finger, this finger. So imagine like a tree, you have all these branches, and each branch has more branches. So those fingers are reaching out into space, searching the entire space. So those are known as probabilistic searches, and MATLAB has two of them, the PRM, the probabilistic roadmap, and then it also has RRT, which is randomly something. We'll remind ourselves when we get to the slide. I don't use them because I find A star, which is the best traditional path planning algorithm, quite adequate. So I haven't found the need to go to RRT. So somebody got their PhD on the RRT algorithm, this random search. Now, if you don't throw out a lot of points, you will get a suboptimal solution. Because if you just say 10 points, right, it's not going to have the resolution to search out the space. The more points you throw out, the more guaranteed you are of getting an optimal solution. So that's the classical trade-off. Do you throw 10 million points? No, it might be a waste, right? So you have to assess your task and figure out what is a good result for you. So you have to make a choice, how many sample points are you going to throw out there? So again, let's remind ourselves the vehicle needs to move from current location to destination to an environment that is partially known or completely unknown. So you know what happens when an environment is completely unknown? There's nothing that is completely unknown, because if you turn on your sensors, at least you can see locally to the extent of the sensor horizon. So you have your local map, but the rest of the horizon, you don't know whether it's empty or completely blocked. The standard assumption is to assume that anything that you can't see is empty. That's what you do. So then when you path plan, what will happen is, remember I told you the straight line segments are connected at odd angles. When you reach the horizon, the sensor horizon, because you are making the assumption there's nothing there, it will shoot one line through to the final destination. So, but then, is it time to relax? No, because as the robot moves, right? As the robot moves, the sensor horizon is going to advance. And when the sensor horizon advances, it's going to see new obstacles. Unless there are no obstacles, it's going to see new obstacles. And therefore, you'll find that last segment being replanned. So the line that went straight to the goal will now be bent around the goal. And then if you see more obstacles, it will be bent again. So that's how dynamic path planning happens. That's what happens when we move. Because we only have a local map, right? And as we move more and more, we see more and put it on the local map. So that's what happens with unknown territory. The path is constantly being replanned. So types of path planners. So you have search based, and that's purely deterministic. So deterministic means everything is ordained. If this happens, then do this. If something happens, do this, right? So it's like a plan made out for you by your parents. It's so precise. That's what a deterministic planner is. It is associated with the sense of mathematical rigor and optimality. There's the word again, optimality. So a deterministic system or algorithm is a system in which no randomness is involved in the development of future states. So it is perfectly predictable what you're going to do next. So the future states, steps of the system or algorithm. On the other hand, sampling based or probabilistic, another word for it, path planners, associated with a sense of randomness. So it is like rolling the dice, but not like Las Vegas, not that bad. It is intelligent, but it's still, there is a randomness involved in it. You will find the path, but to what level of accuracy depends on how many points you use for sampling. So generally this is going to be faster, and generally the better plan is going to emerge from here. So this is going to be faster provided you don't use like 10 billion points. If you don't overdo it, yeah, it's going to be faster than the other method. So let's take up the more traditional graph-based path planning. So we need a strategy or model for representing space in environment that is either free or occupied. I may have talked about it earlier, but I was hand waving. I have a picture here, and I'll show you, exactly how you obtain a model, the most common model for representing the environment. The map is a model of the environment. The map only contains, those aspects of the environment that are important to solving a problem. Color of obstacles is not important to navigating around them. So you won't put the color of obstacles, right? So that's what I mean by a model. It's a map. What is your mapping strategy? Then after that, we're going to take it and convert it to a connectivity graph. You'll see what a connectivity graph is, and then the optimal result will immediately emerge. So connectivity is basically, you see, is a method of representing relationships. So first the map. So the occupancy grid map is the most common form of map used. So essentially it uses the space, it takes a space and breaks it up into tiles, Gazebo has a 1 meter by 1 meter tile. This is about like maybe 20 centimeters by 20 centimeters or something. So that's what these are. So you can see there's a lot of memory involved. So there is another style of mapping, which of course is a product of academia, universities, but nobody uses. It is really more brainy, but because people writing algorithms like to get the job done quickly, they use this. So even though this uses a lot of memory, conceptually it's easier to deal with. But somebody said, there's so much space that is empty, so why are you wasting tiles to represent empty space? So so then you have to break down the space in an intelligent way and figure out how to separate the empty regions from the occupied regions. So that requires more of brain, at the beginning. It's too complicated just to save some memory, right? And memory is so cheap these days, people said, okay, go publish on papers, but we're not going to use that method. So there are all these interesting methods in the literature. So we've seen this in the G-mapping demo yesterday, but this is what you end up with, this is not related to this, but that's what you'll end up with. So the walls are black. Why is that? Because we take multiple samples of the wall over each pixel, wherever the wall is. And therefore we are confident. We count up basically every time the LiDAR sees something on top of that pixel or cell, it counts up. If you allocate 8 bits, then you can go up to 0 to 255. But see, the memory is building up already. 0 or 1, occupied or not, is much easier, right? But 0 or 1 is too crude for driving. So you would prefer to have a finer resolution. So sometimes you allocate 8 bits. If you want a better way of representing it, you can go with 16 bits. That's a lot of memory now. 2 bytes for each cell. So it kind of builds up in a hurry, because imagine the VIT campus size and imagine these tiles, and now you need a lot of memory. So how do you get to that? Well, let's assume that you have a LiDAR. Well, could be a sonar, because the LiDAR pretty much will have a wider range than this one. So let's assume it's an ultrasound device. So what it's doing is it's sampling the space around it, and it is quite sure that all this stuff right here is known, and that is known also, but it's occupied, right? So this is a binary map. But how will you get a ray level map? So a ray level map, depending upon the counter, right? Unless the counter reaches 255, you won't make it black. So 0 will be white, 255 will be black, but anything in between depends on the count. It will give you different gray levels, and that is what is going on here, except that it has seen all the space here, so it's whitened. But you know what I mean? Like maybe it has sampled one particular area less, so it will be a gray level, but here probably it's gone enough around the. So if you go on the internet, you'll find cases where you get gray levels here, but here it seems to be certain because it has sampled all of that. So that's what an occupancy grid is. So it also helps you, as I said yesterday, eliminate moving obstacles, or like animals, right? Or human beings, pedestrian crossings, pedestrians crossing a road. So you can count up and then you can count down and remove it from the map. Otherwise the whole map will be filled up. If you don't do that and you have moving obstacles, then you will permanently be putting them on the map. Okay, the connectivity, remember a few slides ago, let me remind you. Convert the map of the environment into a connectivity graph and then try to figure out what the optimal path is. We're going to do it right now. So this is a historical method. It lines up very much with human intelligence. So imagine that these are buildings, right? And you have to go to the other side of the campus. You're starting here and you have to go there. You're allowed to walk across the grass. You don't have to stay on the pavements, right? So what would you do, right? It's dark. You'll keep on walking until you hit a wall, right? And then, no. I'm thinking of the bug algorithms. What you would do is, you would curve around the building. So you'd go to the corner of the building, right? And then you'd go along the face of that side of the building. And then you would try to go directly towards the goal. And then you would go to the corner of the next building, because you have a map. So if you look at it, all the possible roadways are shown here. So for instance, you can go like this, and then hit this corner, or you can go hit this corner and go to the goal. So essentially you create a roadway network initially. This algorithm is not difficult because it works off, see, all the obstacles, they have been, even though the building might be curved, no, you force a bounding box that is made up of straight lines, because otherwise this algorithm will not work. You can't have curved sides to the building. So then all the roads, quite a big network of roads is created by joining every corner to every other possible corner. Now you won't join this corner to this corner, right? Because it's going through an obstacle. So you will join corners only if it's in empty space. So we join this, we join this, we join this. You get it? So you extract all the possible roadways, roads in quotes, because these are not really roads, but they're like roads. And then a graph search algorithm will reveal what is immediately obvious to a human being, that this dark line is the best path. So it's very intuitive. It's how human beings would solve this problem if they have a map. They would go to the corner of the building and then they would go along the face of the building, just like this. Well, here there is no going along the face, but if the goal was somewhere here, they would have gone along this face, right? So it's probably 2 or 3 decades old, but it's nice to establish the concept of a graph, right? Nodes and connectivity. So this is the first exposure that I give to my students on what a graph is. Now this is not a graph-based method, but I like to throw it in there because it creates a model of the environment based on charges repelling and attracting each other. It's actually, this idea has lived on because, as I said, in universities they try to develop it, and quite recently there was a paper improving on the original potential field method. So let me explain first why they use the word potential. It's a natural method. It's trying to model the environment in terms of the physics of charged particles. We know that light particles repel and oppositely charged particles attract. So that's what is going on here. Goal attracts robot. So what they do is they give the robot and goal opposite charge. Now we'll get to this, but the difficulty is how much charge, because this is not a natural charge repelling and attracting situation in physics, right? You're trying to act as if the robot has a charge and the goal has a charge. So somebody has to assign this charge. And so in the early days, people got stuck with how much charge to assign, and that's why you get a succession of papers. People figured out, okay, here's my algorithm for assigning the right charge. I'll tell you what happens if you don't assign the charge. I'll tell you in a second. Uh, so, so by doing that, right, the obstacles are what? Same charge as the robot, because you want to push away from the obstacles, and the goal is opposite charge, right? So you know that there is this electrical field force Q1 Q2 by R squared, and then there's an epsilon or something, maybe. But so you use something like that. The electric field. So the electric field is actually, these are fields of equal potential. This is the electric field which is perpendicular to the lines of equal potential, right? And so what happens if you do it right, the robot kind of rolls down a hill of potential. The robot goes down a hill of potential all the way to the goal. In practice, what happens is, if the charge is assigned to obstacles and the robot and the goal is not right, sometimes the robot will balk here, because you can see an opening, right? But it's working off fields and forces, electric forces, right? So the force is, saying you can't go here. And that's because you haven't assigned the right charge. So the method will work only if you come up with a good algorithm for assigning the charges. And that's why people keep on publishing and saying, try this. And now, of course, with machine learning, I bet you there'll be a machine learning approach to assigning the charges. Because, that's another paper that somebody will get. But we actually tried it out. It's difficult to assign these charges without reading further. And the robot kind of flows like water down a hill. It flows down the hill of potentials, basically. You can think of all these equal potential lines as height on a mountain. So the robot rolls down the hill towards the bottommost point. And the beauty of it is, the thing is, it's not always good to get obsessed with the product, but at the same time, it's not always good to be obsessed with the theory. You got to be somewhere in between. So they actually point out that the natural control law for driving the robot is built into this algorithm, because rolling down the potential hill is the control law, right? Because it's keeping you away from the obstacles, right? That field is preventing you from hitting those obstacles if the numbers are properly assigned. So the control law for driving the robot is built into the algorithm. Now, of course, if you say you don't know the map and suddenly you see a new obstacle, you have to figure out, okay, what are you going to do with that obstacle, right? I told you, we don't know the whole map, and sometimes when you go around a corner and you see a new obstacle, how are you going to assign the charges? I bet you somebody is published on that also. So, the potential field method. So, the limitations of the potential field method is that the parameter assignment and tuning, charge assignment is really, there's no rule unless you make up one. Sometimes the robot can get stuck in a local minima. That means it's like a hole on the side of the mountain, right? You're going down the mountain, but locally, the ground goes up that way. So if you roll a ball, it's stuck in that temporary hole, if you know what I mean. That's called a local minima in the terminology of optimization. So they have algorithms that push the ball a little bit, hoping that it climbs over that little height increase, and then it starts rolling again. But how much to push it? Because if you push too much, you might just, make it jump right over, several features in the landscape. So they call it a momentum factor in MATLAB, and they have a parameter that you can tune. So hesitancy in traveling through narrow paths, I explained the reason why. It looks obvious that you can go through, but the field is not allowing the robot to do so. So by the way, if you have a method that will find a solution if there's a solution, it's known in computer science terminology as a complete algorithm. So that means if there is a solution and the algorithm can find it, it's known as a complete algorithm. If there's a solution but the algorithm could not find it because of the characteristics of its implementation. I gave you an example, right? You expand obstacles by half the robot size, and that sometimes blocks openings, and it may block all openings to the goal. So in which case you call it an incomplete algorithm in computer science, because it's an algorithm that might sometimes fail even when a solution is available. That's the point they're making. So they're saying, watch out, it may tell you that you can't proceed, but you may have to switch strategy because maybe there's a solution available. So the same slide, I like to remind students about this, so I just got it back here again. So we are going to go through the Dijkstra algorithm. Let's take a break, and then when we come back, we'll go through the Dijkstra algorithm, which is reference 2. And we might also take a look at the A-star algorithm, set it up for now, and then on Monday morning we can finish it up. But essentially, let's take a break because I need to go to the toilet, and then we'll go through the Dijkstra algorithm. So Dijkstra is known as the father of graph theory. Edward Dijkstra, he died this century also, just like Kalman. So two famous guys, who are known for what they did, died this century. Kalman was more recent because I remember seeing that President Obama gave the presidential, it's not the Medal of Honor, it's something, Medal of Honor is for military veterans. This is for scientists. So he died in 2012 or 13 or something. Dijkstra died, I think, a little bit earlier, like 2005, 6, I'm just guessing. So we'll come back and take a look at it. Okay, let's go to reference 2. Must be on the next. Yeah, here it is.
To understand what Dijkstra's algorithm is and how it works, let's start with a scenario. Let's imagine that we have a variety of different towns scattered in different locations. Some of those towns are connected to other towns with roads, such that we could travel along a road to go from one town to another. Not all roads have the same travel time, though. One road might take 3 minutes to travel through, while another might take 4. And our question is this: what's the fastest way to get from town A to town B? This is a specific example of a more general problem in graph theory, where we have vertices, in this case our towns, that are connected by edges, in this case our roads. Together, the vertices and edges form a graph.
So this is the core principle. You have to have a graph. You have to break down the problem into a graph. Otherwise, you can't use graph theory, obviously. And you'll be surprised at how many applications can you solve a graph theory. So the whole idea of you have a company with a fleet of airplanes, United, let's say, because the US carriers have like sometimes 300, 400 planes. So how do you determine the best schedule for them? Right? Because typically they don't just go to one destination and back anymore. They go like this. They want to keep the pilots and crew occupied all the time. So they go from multiple. So how do you figure out what is optimal? Without stepping on each other's toes. You don't want to have empty seats. So that's actually solved by a very sophisticated version of Dijkstra's algorithm.
In particular, this graph is
a
weighted graph, because each edge has some value or weight to indicate how costly it is to travel along that edge, measured in either distance or time. And with this graph, we'd like to determine the shortest path from one vertex to another. So how does Dijkstra's algorithm allow us to do this? Ultimately, we need to figure out how many minutes it will take to get to town B. In doing so, though, it might be useful to figure out how many minutes it would take to get to the other towns too. So ideally, we want to label each town with a number representing the shortest time required to get there. But of course, we don't know that information yet. So instead, we'll label each town with the shortest time we've found so far to get to that town. Before we've started the algorithm, we don't have any known way of getting to the towns, so we'll label them all with infinity. The only town that we can label correctly is our source, town A, which we can easily label. We're starting there, so it takes 0 minutes to get to this town. Once we've found the shortest path to a town, let's call that town explored. For all other towns, we'll consider them unexplored. We don't yet know what the shortest path to them is. So what can we do next? Dijkstra's algorithm repeats a 2-step process. First, we update our estimates, and second, we choose the next vertex to explore. So let's start with the first step, updating our estimates. We know we can get to town A in 0 minutes, and because we can get from town A to town C in 3 minutes, we know we can get to town C in 3 minutes. That's much better.
Oh,
current estimate of infinity. So we'll update our estimate to be 3.
Okay. Is that permanent? Hardwired, cannot change? This number 3?
It's not permanent.
It's not permanent because you could probably try getting there from other cities, right? So that's exactly the problem we have in moving around between cities. So, but this is not restricted to just cities, it could be waypoints. So, because, let me tell you, it may be that it's shorter to go this way. So you got to try that, right? And he's got an organized procedure for doing it. Not only that, traveling from here to there might be different from traveling from there to here. Why is that? So in the US, in many places they have this system where they will allocate the lanes going in one direction based on the time of day. So typically in rush hour, everybody's going towards the city. So if there are tunnels, they'll say 2 lanes going this way, only 1 lane coming this way. But in the evening, they will reverse it. So the weights are not necessarily the same in going from here to here as from going from there to here. So this one doesn't show that, but all you have to do is add another edge with an arrow on it indicating which direction you're traveling and put a weight next to it. So Dextras can handle that also.
And we can do something similar for town F. We can get there in 2 minutes, so we'll update our estimate. After we've considered all possible roads
So what is the
connecting
best?
to town A, we're done with.
Anybody can tell me? Which one can now be labeled as explored? This one. The smaller of the two, right? Because no matter what happens, the distance from here to the starting city cannot be greater than 2, right? And you know why that is so? One of the conditions of Dijkstra's graph algorithm is that you can't have negative nodes. So if you had negative nodes, then it might be possible to beat 2, because somewhere there might be a negative node. But that's why the Dijkstra's graph assumes that the weights are always positive. So now you can conclude that, okay, this can join the explored cities list.
This step. And now the next step is choosing which town to explore next. And the rule is quite simple. The town we explore will always be the unexplored town with the smallest estimate. In other words, the next town we explore should be, among all of the unexplored towns, the one we know we can get to the quickest. In this case, that's town F, which we can get to in 2 minutes. And now, the 2-part process of Dijkstra's algorithm repeats. We first update our estimates by looking at the towns connected to town F. It takes 5 minutes to get from town F to town G. So if we can get to town F in 2 minutes, then we can get to town G in 7 minutes.
5 plus 2.
The sum of those 2 values. Likewise, we can get to town B in 8 minutes, and we can get to town E in 5 minutes.
Now,
We can also get to town C in 4 minutes.
should we change
2
that?
minutes to go from A to S, and then another 2 to go from F.
We should change that, because
But
3
4 minutes is
shorter.
actually more than our current best estimate for town C,
So don't do
which
anything.
is 3 minutes. So we don't want to update anything here. Remember, for each town, we want to store our best estimate for the shortest amount of time required to get there. So let's keep going. The second part of Dijkstra's algorithm tells us to explore the unexplored town with the smallest value. And in this case, that's town C, which we can get to in just 3 minutes. And the process repeats again. Going through town C, we can get to town D in 7 minutes. And we can also get to town E in 4 minutes. 3 minutes to town C, plus 1 minute from C to E. That 4-minute estimate is better than our current estimate of 5 minutes. So we'll update our estimate for town E
Okay.
from 5 to 4. The next town to explore is town E. Among all the unexplored towns, it has the smallest value. Notice that each time we explore a new town, it's guaranteed that we will have found the shortest path to get to that town. Since if there were some shorter path, we would have explored that shorter path first, because we prioritize exploring these smaller values. And through town E, we can get to town B in just 6 minutes. 4 minutes to town E, plus 2 minutes to go from E to B. So we update our estimate for town B to be 6, which is better than the previous estimate of 8. And now, the next town to visit is town B, our destination. And that tells us that the shortest time needed to get from town A to town B is therefore 6 minutes. And that's Dijkstra's algorithm for finding the shortest path in a graph. Now, there are a few things worth pointing out here. The first is that technically, our algorithm has only given us how long it will take to get from town A to town B, and it hasn't actually given us which path to follow. In order to actually reconstruct that path, we'll need to add a...
So that is known as backtracking, because you have the smallest number, but that smallest number came because of a certain pattern, right? So it's possible to go backwards and extract that path. It's known as backtracking. And
That's
what it's going to talk about.
Every time we update our estimate for a town, we should also keep track of what previous town we visited in order to get to this new estimate. If we keep track of that for each of the towns as we progress through the algorithm, then at the end, we can figure out what the best path is just by following those arrows backwards to the beginning. Also, it's worth noting that this algorithm only works correctly if the weights of all of the edges are non-negative, since otherwise some negative length path might result in a shortest path that our algorithm wouldn't be able to find. Another thing worth thinking about is how we efficiently determine which unexplored town to visit next. We want to always pick the unexplored town with the current smallest estimate. So some kind of priority queue that gives us efficient access to the next town to visit can make our algorithm faster. And that's Dijkstra's algorithm for...
Okay, so it's quite natural, right? But he came up with it, I would say 1900 and something, like he was probably 90 years old when he died, so probably 1840 or something. The Dijkstra algorithm was 1940 rather, the algorithm was proposed. Okay, so I want to show you one other algorithm, and it's the one that many hobby roboticists use. So this one is used by, so one of the problems with this is, whether you like it or not, it's going to give you the best path, the starting node, to every city. So sometimes in robotics, you don't need that. You want to know how to go from this cell to the goal cell. You're not interested in generating the best path to every other cell in the environment, right? But the Dijkstra algorithm, the way it is formulated, it forces you to explore a good part of the environment. And so A star doesn't do that. You see A star on Monday, so that's why A star is good for robotics. Dijkstra is good if you're saying, okay, I have a robot here, and I need to know how to get to every corner of this environment. Maybe there's a need to do that, then Dijkstra is better. If you're just going from point A to point B, then it's better to use A star. So let me find another algorithm, it won't take long, and then we'll call it a day. And the one I'm going to show you is computationally very efficient. It assumes you know the map though. It's from a different PowerPoint set, but I meant to import it, but I did not. I hope it's here. So it's got a number of names, NF1, brush fire, flood fill. You'll see why the last two names, NF1 sounds like, some scientific guy, came up with it. I don't know what the expansion of that is. Brush fire and flood fill make a lot of sense. So, a known map, right? So here is the goal, and the destination is here. Start at goal and fan out like a fire. That's why you call it brush fire, because if the grass catches fire and if there's no wind, the fire is going to advance equally in all directions. And that's how this algorithm will work. It will spread out in an even fashion. So start at goal and fan out like a fire. Each cell's Manhattan distance to goal shown. You know what a Manhattan distance is? So Euclidean distance is square root of x2 minus x1 squared plus y2 minus y1 squared. But if you're in New York City and you're asked to go there, the assumption is you can't cut through buildings. So you'll have to go this way and this way. So this is called the Manhattan distance because you're only supposed to walk either in the x direction or in the y direction. that is known as the Manhattan distance. So we start here. So you see 1, 1. So the fire is fanning out. Similarly, if you think of water causing a flood, and there's no tilt in the ground, it's going to go evenly. So that's why they give these names, much better than NF1, I think. So here start at 1, and then you go 1, 1, right? So diagonal motion is not allowed here because you're going to cause confusion. Why is that? Because the diagonal length is 1.414, square root of 2, and that causes a mess. So they actually don't want that. They want integer numbers. So you can only get there by getting here or here. So once you have filled out all the ones, filled out the next step. So there's a 2 here, right? And a 2 here, got it? Because from the 1 here it's a 2, from the 1 here it's a 2. So but there's also a cell here which is also 2. Obstacles are not traversed because the robot is not meant to go there. Then you do a 3, there's only one cell, right? And then you do a 4 and a 4. So you can see the flood is filling. A 5, and then a 5 also here, a 6 and a 6, a 7 and a 7 and an 8, and you can fill out the rest of it. Then when you reach the, you start from the goal and you reach the origin. From that point onwards, what is the best path? You will count down this number 8 in the most optimal way. So for instance, 8 becomes 6 here. So it's a bit of a contradiction. Initially, he's not labeling the diagonal cells with a square root of 2, but in counting down, he allows a diagonal jump. Computer science algorithms don't have to make sense in the real world. They're just a rule that works. So he goes from 8 diagonally to 6, down to 5, down to 4, diagonally to 2, sideways to 1 and 0. So in fact, there are many robotics algorithms that use this robot projects in universities that use the flood fill algorithm. Yeah, go ahead.
So even if it is in diagonal, but that's a 6, it's not 7, right? So why he omitted the 7 into 6?
So because he's interested in reducing the distance from the starting point to the goal as fast as possible. So he allows diagonal motion because it gets from 8 to 6. Instead of 8, 7 to 6 will be a longer path. So sideways and this way, now he says, okay, there's a longer path, let's cut across diagonally. So the beauty of this is, I forgot to tell you, Dijkstra's algorithm, they have a thing called O, the O number. So the O number means what is an estimate of the amount of time an algorithm will take. For Dijkstra's algorithm, it is the square of the number of cells. So in Dijkstra's algorithm, you count the number of cells and you square it. So which means that if you double the number of cells, it's going to be 4 times the time taken to solve the problem, right? And so you can imagine if you have all of DIT and you're trying to solve it by Dijkstra, it's going to take enormous amounts of time. This one, it's order of the number of cells. So the flood fill algorithm only takes as much as the number of cells, So immediately it is better than Dijkstra. But if you want an algorithm that finds a path between the current cell to all cells, then it's better to do Dijkstra because you need that then. Because this only gives you, point to point. It does not give you all cells. So they use this a lot in video game theory because they have this situation where there is a knight, a hero, and then the villain. So you have to go around obstacles, to get there to kill him. So this is how they figure out the paths. Because the scene is constantly changing. So there is no one path. Maybe the villain moves there, right? And maybe suddenly a doorway that you thought was closed opens. So based on that, you get different paths and you have to solve them quickly because game machines don't have that much power. I'm talking about the ones that, not the computer, but they have many in Las Vegas where you can stand and play a game by putting money into the slot. So it has to go fast. So they use this in gaming a lot. So this is it. You can go, there's an excellent example here. Start searching for best path from goal, working back to starting position. Each cell is visited only once. That's why it's order of n. And the complexity is not related to the obstacle density. The complexity of the algorithm will not change no matter how cluttered or empty the space is. It assumes the map is available. So, and on Monday we'll look at A star. So that is the pinnacle of all search algorithms. Anything that came afterwards was just to make it faster or to get it to deal with a situation where you have a changing map. So you do have a changing map, right? Because you don't know the whole map. As you advance, your sensor horizon goes further and further and you discover it. So in A star, when that happens, you basically from the point you discover something new that is blocking your original path, you run the algorithm again from scratch. You basically close the program and start it again. Somebody, and that person came up with D star light, said that, hey, you don't need to close the program because if you save some cell values, I can just alter those cells affected by the new obstacle. He found out that only a few cells their values need to be changed. The numbers need to be changed. So he came up with D star light. And but other than that, the concept is if you ran A star again, you would get the same results as D star light, running just once. So it's just an advantage in implementation, but you get the same result. So I consider A star as the pinnacle because not much is new. This probabilistic method is not really competing on the same level, right? Because it's saying that you have to throw out a certain number of points, and if you do, you'll get a solution that is close to the optimal, but maybe faster. So that's what they're claiming. So it's not really a new algorithm, it's just a different way of doing it. If speed is important to you, you might try the sampling method by throwing out points there. But then people will say, okay, how do I know I have enough points? And most people will overdo it, because they don't want to worry about, okay, what is the right number of points? So they say, I just send 1 million. They'll be slow anyway, because they're sending 1 million. So, all right, so I'll see you on Monday then. Okay, so you'll be able to finish the homework, right? Yeah, I'm going to show you the solution, not the code.
Okay.
But the solution, solution meaning you're going to see the robot Momo. That to convince you that, yeah, it is going to work. So the code is going to remain here. The reason I'm showing this to you is, it worked about 2 weeks ago, it's still working. It worked except for one glitch, and I said, okay, I'll fix that later, because it's not that important. So I'm going to pose a question to you which might help you in your debugging as to what is the plot looking as if it's missing something, and then we'll answer that question. If you can't answer it, I'll try to answer it for you. So typically this command is available somewhere in the past. There it is. So watch. There's nothing to see until I minimize this. Okay, hopefully you can see all the waypoints. Remember, one was somewhere there, and one was here, and the last one was here. Okay. So okay, just watch. With my luck, it'll crash now. And the word will spread in the student body that, hey, even the professor couldn't get it working. See? It's running. So that's what your answer should look like. What was it? 2-4? Yeah? Minus 2-4, I think. And I think it's going towards the 4. It did, see, it's taking a turn. Because the new heading, right? I think the other one was 3-2 or something, I don't remember. Somewhere there. Maybe 3-2, I think. 3-2. See? And then it'll stop at 0-0. I'll show you the plot, and you can tell me why it seems incomplete. Okay, look at the plot. So we started 0-0, right? 0. So why these incomplete sections? So remember, we have the for loop, but then we have 2 loops. One is distance to checking whether we get inside that circle. but we also have a heading loop, right? So the points are being generated all the time. So you got to pick them up everywhere. So I didn't copy the plot accumulation within the heading adjustment loop. That's why now, but then should it miss points all over? No. Apparently, when you're far away from the point, either that or the other way around. Okay. When you're far away, there's not much heading correction, so it's not going into the inner loop. But when you're see the angles, you can tell by the angles, right? Draw a line from the robot position to the goal. So one of them, it's more sensitive. It's doing more of the inside while loop. So when it goes there, it misses, and when it's outside, it collects it because I have the plot collection points, there. Right? I just have to copy and paste it in a different spot. So you can tell the receiver robot did everything. So this is just a plotting error, right? And there are a few points, you see. It needed to go, and then it picked up the point, but then it's not doing it consistently because I don't have that plot collection going on within each loop. So you have to remember to do that, otherwise you get a plot like this.
So last time also we ran the bot in L shape, but
Yeah.
we didn't get an exact plot that the robot went into. So we just got an arc
Okay, for this problem?
for the first assignment.
For the first, oh, okay. Oh, you didn't get a L shape?
No, actually, bot was running in L shape.
Oh,
The plot was not showing.
So is it because you did not pick up all the points maybe?
Yes.
Okay.
Maybe.
You found that out later?
No, while doing it, so we found it out, but unfortunately, we had a less time to submit it.
Okay, I got it.